Good afternoon, everyone. I'm Dave Ballo from Agilent Technologies in the Santa Rosa division, and I'm an application engineer for our network analyzers, the PNA family of network analyzers in particular. And I'm going to be talking about noise figure measurements today and optimizing. They'll have a section talking about on-wafer measurements in particular. So this presentation is actually a subset of a longer paper. And so if you are interested afterwards, you can contact me and I can give you the full paper that this microapp paper is a derivation of. So it's basically broken into 4 sections. The first section here, I'll give a brief overview of the way the PNA-X measures noise figure, because it's a little bit different than what's been the industry standard for many years, which is the Y-factor method. Then I'm going to talk a bit about how we characterize the noise receiver. We have a new measurement methodology that does that. That is essential for making noise figure measurements. And then I'm going to be talking about the on-wafer applications and getting the accuracy that we have right to the probe tips to do the on-wafer measurements. And then the last part of the paper, which I'll probably have to go through fairly fast, is talking about what to do in the 50 to 67 gigahertz band, because things are a little different there. So noise figure, hopefully all of you are aware of this. It's a really useful figure of merit, and it's an industry-wide standard, and it simply characterizes how much noise any active device adds. It can be an amplifier or it can be a frequency converter. It's a very nice, intuitive figure of merit because it's defined just in terms of signal to noise ratios. So if your amplifier or converter is adding noise, the output signal to noise ratio is less than the input signal to noise ratio, which means the noise factor is greater than 1 or the noise figure is greater than 0. It can mathematically be expressed in this sense, where you can just, if you know the gain of your device and you know what the input is, this is normally KTB, that's how much noise you would expect at the output if it was a perfect device. If you ratio to the actual noise output, that will give you an indication of your noise figure. And this formulation of noise figure helps explain how the PNA-X actually measures noise figure, because we can measure gain using S parameters, and we can measure noise output as a second measurement, completely independent measurement, and calculate noise figure. Now, one point that I do want to point out here is noise figure is defined in a 50 ohm environment. So the degree that your test system is not 50 ohms, that can introduce measurement uncertainty. And it can be quite significant if you don't do some error correction to take care of those. So what's been more the traditional way to measure noise figure is what's called the Y-factor method. And this is the method that I'm sure any of you that have measured noise figure are familiar with. It's using a noise source, which consists of a diode, a special avalanche diode that's optimized to generate a lot of noise when it's in breakdown mode. And so this diode provides both the room temperature termination, and then when you turn on the diode, it gives what's called a hot noise. And that amount of excess noise is something that's specified by the noise source. And with this method, you're actually measuring both the noise coming out, you get noise figure and you get the gain of the device. And you really need both of those pieces in order to calculate noise figure. The PNA uses what's called the cold source method. And as I said before, the gain and the noise power are measured separately. So the gain is measured with S parameters, and we use the standard NA receivers. And then we turn off the sinusoidal sources. We switch over to our low noise receiver, and we make one noise power measurement. So we do not use this during the measurement. And this method allows noise figure to be integrated into this test system very nicely, and with a single connection to the DUT, we can make a lot of different measurements. Now, we have some really advanced error correction that we base it on an impedance tuner. The PNA-X gets very high accuracy noise figure measurements due to a lot of advanced error correction. And so I'll talk about that briefly in a second here. So the Y-factor method, it does a pretty good job if you can hook the noise source directly to the amplifier under test. But when you're on an on-wafer environment, this addition of a cable here and a probe degrades the source match of that noise source. And that will cause measurement error. And things get even worse if you've got a switch matrix as part of your measurement setup and you're trying to do Y-factor. So the PNA-X, because of this advanced error correction, is able to give high accuracy in all these environments. So the way we do it, this is a kind of a brief summary. It's described in an application note that we have out on our website. But the idea is that we're trying to measure noise figure right at 50 ohms. So this Smith chart is representing the source match that we're presenting to the device under test. And we want it to be exactly 50 ohms. But any RF or microwave designer knows that you can't build a perfect 50 ohm source match over a broad frequency range. So rather than assume we're right in the center of the Smith chart, we actually present a series of known impedances. We can either use an eCal module. Some of our PNA-X's have a built-in tuner. But the idea is that if you can measure noise figure under a set of known impedances, and the minimum you need is 4 impedances. In practice, we do anywhere between 4 and 7. You can choose that. But if you measure the noise figure at each of those impedances, you essentially know the noise correlation matrix or the noise parameters of the device that you're measuring, and you can calculate the 50 ohm noise figure. It's a very effective way of overcoming imperfect system source match. And we do that over frequency. And the result is that we get some very flat measurements here without ripple. And this is a Y-factor measurement of an unmatched device. So in this example, we've probably picked the hardest device to measure. It's a broadband device. This goes up to 18 gigahertz. And it's completely unmatched. It's a bare transistor. And the Y-factor method had a lot of all this ripple is essentially measurement error. And the error correction the PNA-X is the blue line, and we've removed that systematic error. So it's a combination of correcting for classic sinusoidal mismatch as well as correcting for noise parameter related errors, where the sensitivity of the device under test, its noise figure versus impedance sensitivity and variation, that's what we're correcting for. Okay, so that's showing the Y-factor, and there's the PNA-X method. The problem with the Y-factor is you often don't realize how much underlying measurement uncertainty is there, because either you've undersampled the data, you don't see the ripple because you haven't taken enough points. This was a 401 point measurement. Or you're acquiring data over a narrow band and you don't see the ripple. But this shows there's still underlying measurement uncertainty. Now in this case, it's plus or minus half a dB or more. It's not always that bad with Y-factor. It depends on a lot of things. But the takeaway is that the PNA-X corrects for these, so it works in a much broader range of environments, basically any noise figure environment. A little bit of what's new. We have now a new 50 gigahertz noise receiver. We're showing that here at the show. One of the nice things is the impedance tuner that we use as part of our vector noise correction is now built in. And it's also that hardware is available in the 67 gigahertz PNA-X, but it only works to 50 gigahertz. So between 50 and 67 gigahertz, you have to use the standard NA receiver. And the noise figure of the standard receivers is actually pretty bad. It's 40, 45 dB noise figure in that range. And that means that in many cases you have to add an extra preamp to cover this band here. And I'll talk more about that in the last couple minutes of the paper. You can see with the low noise receiver, this is up to 50 gigahertz, we get about a 10 to maybe 12 dB noise figure at the test port. One of the really important things about measuring noise figure is characterizing the receiver's gain and bandwidth. So the noise contribution of the noise receiver, whether it's an NFA or a PNA-X, it has to be known, and then you subtract the instrument's noise from the raw measurement and to get a corrected noise figure of just the DUT. And so the measured power of a noise receiver is affected by its gain, its bandwidth, and its noise figure. So we have to actually, as part of our calibration process, characterize that. So obviously more receiver gain means you're going to measure a higher amount of power in the receiver. More bandwidth also means more noise power. So one of the principal things we have to measure is the gain bandwidth product of the receiver. And those can be either measured separately or together as one product. And the noise source method actually is measuring gain bandwidth product as one term. It doesn't separate out gain and bandwidth. And it does that by using a known amount of power coming out of that noise source. Now the PNA-X has a new power meter-based calibration method where we actually separately measure the gain of our noise receiver and the bandwidth. So the way it works is that you take a power meter and you calibrate one of the RF sources inside the network analyzer, and then we can take a calibrated source and use it to calibrate the gain of the noise receiver. So if we put in a known power and we see what the noise receiver is reporting as the measured, we know what the gain is. And so that gives us the gain piece. How do we measure the bandwidth of the receiver? So what we actually do as part of this power meter-based cal is we do a frequency sweep of the noise bandwidth that we're using. And so we get something that looks like this response. This notch here is actually essentially a DC, because it's a homodyne receiver. So we measure that at each frequency point of the measurement, and then we just calculate the equivalent rectangular noise bandwidth. So we've got the power meter piece gives us the gain, sweeping the filter gives us the bandwidth, and then we know the gain bandwidth of the receiver. So this is an alternate method to using a noise source. And you as a user would have the choice of using a noise source or using the power meter approach. The power meter-based approach at a high level gives you the same, or in some cases better accuracy than using a noise source. So the ENR can have a lot of roll-off at the high end, and that's avoided by the power sensor, which is really good. So the power meter approach is a bit better compared to just an off-the-shelf noise source, and it's comparable to actually using a NPL. So this is a National Metrology Lab calibrated noise source. So it's a good method. We've done some correlation measurements here. This is noise figure. One of the traces here was using the power meter approach. Another trace here was using the noise source approach. And you can see at this scale of half a dB that the noise figure overlays very nicely. So it's just a validation that either of these methods for calibrating the noise receiver work very well. So let's talk a bit about on-wafer measurements now. With the PNA-X, there's two different approaches for doing on-wafer measurements. One of the ways is let the PNA-X's firmware guide you through a calibration where you're mixing some coaxial-based standards with your on-wafer standards. And the other approach is to just do your calibration always in coaxial standards, right, which is a little easier, and then de-embed the wafer probes. So in order to do this, to de-embed wafer probes, you have to know the S2P, right? You need the information of the S parameters of the probe. But because probes are pretty stable, if once you characterize the probes, and as long as they're not damaged, they're very stable in terms of S2P. So it's another approach. The only downside of this approach is you have to unscrew the cable from the probe in order to do the system calibration, and then you have to connect it back on. So a little bit of uncertainty, maybe due to connector repeatability, but it's only coaxial calibration. This approach here, you're not having to disconnect anything, but it means you have to go through a full wafer probe. So the choice is yours. Either way works. So the Cal Wizard, it guides you through the steps here. So this is using the Cal Wizard. So here, obviously, the noise source in this example is coaxial. So you hook it up to the cable. I guess in both cases, you do have to break you have to unscrew the cable there to hook up the coaxial noise source. You do a 1-port Cal there, and then you do your on-wafer Cal there. Whereas the other approach is, the first step, of course, is to get the S parameters of the probes, and Agilent has a macro to help you do that if you want to use it. Then you do a fully coaxial calibration, and then you use the fixture feature to de-embed the probes. So I've got some examples here of 2 different wafer systems that we did back at the factory in Santa Rosa. The first set of noise figure measurements we were doing, we were using this automatic probe station that we had access to for that day. And the PNA-X was actually mounted on a shelf back here, and it was not as close as you would like in an on-wafer system, so we had to use some longer cables. And this was the result we got using our more simple error correction method. And you can see it's hard to see the scale here. It's 2 dB per division. You can see there was some ripple in the measurement here. Then we went to our full vector noise cal using the impedance tuner. And from about 45 gigahertz on down, it basically removed the ripple in the measurement. But you see it started to have some problems here with these spikes here. And that was where the vector noise algorithm was failing because there was too much noise in the measurement. So one way to help overcome that is just to do more noise averaging. But I'll show you another technique that also helps. We repeated these measurements a few weeks later on a proper setup, where now the instrument was right above the probe station and we could use some short cables. And in that case, we got much, much better results. Going all the way to 50 gigahertz, you don't see the problems with the big spikes. So the takeaway is that in probing systems, short cables with low loss is extremely important. Now, the internal tuner that helps us gives our full vector error correction, it's got a pretty nice set of impedance spreads at 1 gigahertz. Up at 50 gigahertz, just due to loss, the impedance states are starting to get close together. And if they get too close together, that's when the vector noise calibration algorithm can have a problem. So one of the ways that you can get around this is actually to put the eCal module and a bias T if needed as close to the device as you can. And that will help now get the wider impedance spread closer to the device, and you're not suffering the loss through the test set there. The best approach, though, is to actually remote the directional coupler and the bias T and the tuner. So this would represent really the highest level of on-wafer measurements, both for S parameters as well as for noise figure. So it kind of depends on the frequency range of your setup, the loss of your cables, which is affected by the length and the quality of the cables. In Santa Rosa, we often do this, where we have external couplers because we're trying to get the very best measurements possible. And these are some experiments we did. This was using the first non-optimal setup, and we saw a big improvement here by using the full set of external components. This is a blown up, this is now 0.5 dB per division, and it's showing the effect of using the external coupler, which is here, a bias T and an ecal module, and we've reduced the jitter on the noise figure measurements considerably by doing this. So this is really getting the best measurements. Again, this was up to 67 gigahertz. So I've only got about a minute left or less, so I'm just going to really quickly go over what to do in the high frequency band. Our noise receivers only work up to 50 gigahertz. So, but in that extra band, you've got to add your own LNAs, and you have to add your own filters to remove out-of-band noise. So, in addition, you want to reverse the port 2 coupler. And this shows you kind of a setup where you have a preamp here and a filter. And there's some practical tips here which you can look at on your own on some of the issues to avoid problems during the calibration and the measurement in terms of overdriving things. One thing that's you need to filter out-of-band harmonic noise, and there's some examples here of what happens if you don't do that. It's bad. This is covered in an app note that we have, so you can look at that offline. But what I do want to show you is this, that a set of coaxial filters that are back-to-back make an excellent filter for use in that 50 to 67 gigahertz band. So that's the end of the measurement. So we talked about the new noise receiver hardware, ways of using, extending it all the way up to 50 gigahertz, and also different ways of characterizing the noise receiver. So I'll be back at the booth. If you have any detailed questions, I'll be happy to answer them for you. So thank you.